This is Chapter 16. We're going to look at Section 1 today. We're finally getting into thermochemistry. Today's lesson we will focus on specific heat and also calculations dealing with enthalpy of reactions. This particular lesson I know is very wordy. I will try to highlight the important parts that you need to know from each slide. So, if it's a definition, I definitely want you to write that down. So our first one is the definition for thermochemistry. It is the study of the transfer of energy as heat that accompany chemical reactions and physical changes. So we are going to be studying transfers of energy as heat during reactions. A calorimeter. This is energy absorbed or released as heat in a chemical or physical change. We measure that in a device called a calorimeter. At the end of this chapter, there is some reactions that I would like to do where we look at using a calorimeter. And then you get into your different types of calorimeters. Temperature is the measure of the average kinetic energy of the particles in a sample of matter. So notice that temperature, we'll get into heat also, but temperature is a measure of how much motion is going on with your particles within your matter. The calculations in thermochemistry, we're going to use Celsius and Kelvin temperature scales, and as a reminder, Kelvin equals Celsius plus 273. Heat. Heat is energy transferred because of a difference in temperatures. So heat is actually energy transferred because of a difference in temperatures. The unit that we use for heat is the joule. So joule is abbreviated as a capital J. And energy is always transferred as heat, moves spontaneously from a higher temperature to a lower temperature. So heat energy spontaneously moves from high temp to low temp. So we're finally going to get into some calculations. The first one's going to be with dealing with specific heat. So a definition for specific heat is the amount of energy required to raise the temperature of 1 gram of a substance by 1 degree Celsius or 1 Kelvin. So when you start talking about temperature differences, it does not matter if you're measuring in Celsius or Kelvin, since the difference between them is a factor of a whole number basically. It's not a fraction if you were going between Celsius and Fahrenheit. So you can use either of those, and again, specific heat is the amount of energy required to raise the temperature of 1 gram of a substance by 1 degree Celsius. We do have an equation for specific heat that we're going to get to soon, and this is just giving you the way the units are going to look. Again, joules per gram degree Celsius or joules per gram Kelvin. And again, joules is in your numerator, gram Celsius or gram Kelvin's in the denominator, and those look like they're multiplied together. Here are some common specific heat values for different metals and for water, and a couple other substances in there. You do not need to memorize these values, and again, it's joules per Kelvin mole in these examples right here because they are molar heat capacities. If you need to use any of these values, they will be given to you so that you can pick what to use. As far as an equation goes, there's our equation. C sub P is our abbreviation for specific heat. And you've got Q, which is the energy lost or gained. So C sub P is your specific heat. You have Q, which is referencing energy, which can be lost or gained. You have M for mass. And then notice that is delta T, which is a change in temperature Delta T is the difference between the initial and final temperatures. So most of the time when we're writing delta T, that is equal to final minus initial. So final temperature minus initial temperature. If you rearrange the equation, you get the equation right here at the bottom, rearranged. I don't care which way you decide to remember this equation. It is simple algebra, multiplying and dividing. But some people like to work with everything in the numerator to start with, which is that bottom one. Again, however works best in your mind to rearrange this, I'm good either way. Before we get into our first sample problem, I did want to bring this back up here because you will see us talking about water often. Water, they do give the molar heat capacity of water. I want to focus on water in the liquid phase right here. And for water in the liquid phase, if I gave you just its typical heat capacity, it would be 4.184, and that would be joules per Kelvin gram. So that would be its typical heat capacity if it was not the molar heat capacity. So you will see that 4.184 often, but notice again that the unit, this is per gram instead of per mole like this chart has. So please write down this sample problem. A 4-gram sample of glass was heated from 274 to 314 Kelvin. So that is a temperature increase of 40 Kelvin if you did final minus initial, and it had absorbed 32 joules of energy as heat. The first part of the question is, what's the specific heat of that type of glass, and how much energy will the same glass sample gain if it's heated again from 314 to 344 Kelvin? So let's get started on the math. So part A was, what is the specific heat? So I'm going to write down the equation for specific heat. So C sub P is equal to Q over M delta T. We have the mass is 4 grams. We already have delta T, which is 40 Kelvin. Q is the energy transferred, and they give us Q as being 32 joules in this example. Mass 4 grams. And then change in temperature, we could put in there 314 minus 274, but they've already calculated that as 40 Kelvin. And we are ready to solve. Your final answer would be 0.2 joules per gram Kelvin. Joules per gram Kelvin. So that answers part A. Part B, it wants us to do the exact same thing, but this time the temperature difference is from 314 to 344 Kelvin. So I'm going to go back up here, and I'm just going to erase that 40 degrees Kelvin. We'll see what our new answer is going to be. And this time we are putting in 344 minus 314 Kelvin. And the temperature difference there is now 30 degrees Kelvin. So it'll be 32 divided by 4 divided by 30. So this time, specific heat value, if you had that, that's actually going to be a little different, 0.27, but again, I'm going back and looking at the question. It did not ask for the specific heat value based on that one right there. Part B actually asked for how much energy will the same glass sample gain when heated there. So we're going to use what we did have earlier, which is the 0.2 joules per gram Kelvin as our CP value. And then we're going to go calculate Q. So Q is equal to C sub P M delta T. C sub P is what we calculated earlier as 0.2 joules per gram Kelvin. The mass is still, because it's supposed to be the same glass sample, is 4 grams. And this time the change in temperature, like I showed you earlier, 344 minus 314 Kelvin. And you work that out and you get a value of 24 joules. So Q equals 24 joules And again, grams, Kelvin, all cancels out of what we had originally set up. So we've got enthalpy, which is a word we're going to cover now. The abbreviation for it is delta H. This is the energy absorbed as heat during a chemical reaction. Pressure is going to be held constant. So we typically call it the change in enthalpy. So our enthalpy change is the amount of energy absorbed by a system as heat during a process at constant pressure. The equation that we use for this, delta H, is going to be equal to enthalpy of your products minus enthalpy of your reactants. And exothermic is when energy is released. So in this particular sample right here, energy of the products is less than energy of the reactants. So when you see the positive 483.6 kilojoules and it's on the product side, this will be an exothermic reaction. So in this thermochemical equation, the equation does include the quantity of energy released or absorbed. So that part is going to be important. So thermochemical equation includes energy released or absorbed. And also the coefficients are going to be quite important too, because they're going to tell you the number of moles or number of molecules that you should be interpreting, which will affect this number that you see here for the amount of energy either absorbed or released. So the quantity of energy released is proportional to the quantity of reactions that are formed, or the products that are formed. So you produce twice as much water in the equation that was shown on the previous slide, requires twice as many moles of reactants, and would release 2 times 483.6 kilojoules of energy as heat. In an endothermic reaction, you have higher energy than the reactants, the products do, and the reaction absorbs energy. So in this equation right here, notice it's just water that's being broken down now instead of being produced. So the energy, the 483.6, is on the reactant side. So this would be an endothermic reaction. Again, just making sure you get down the important parts of what's going on. And again, that number is there on the reactant side. But to simplify things, when we do our thermochemical equations, we usually don't write the energy in there as a reactant or product. Instead, you will write it after the reaction like you see here. So the 483.6 kilojoules has been taken out. That's your delta H value. If it is exothermic, the overall reaction, you will have a negative delta H. So if it's endothermic, then you will have a positive delta H. Looking at 2 different graphs right here, this is an exothermic reaction pathway. You can see that your reactants have much more energy than your products. Energy is evolved or given off. And in this one, this is an endothermic pathway, so reactants have less energy than your products, and energy is absorbed. So delta H is going to be positive. Molar enthalpy of formation. This is a change that occurs when 1 mole of a compound is formed from its elements in their standard state. So to talk about molar enthalpy of formation, we use delta H naught is added for the enthalpy symbol, and then F is for formation. Our book does have a lot of standard values. The entries in the table for enthalpy of formation is based off of 1 mole, and formation of 1 mole of a compound from its elements in their standard states. And I will get to what those tables are. If you are in class, you will get a copy of the tables. If you are strictly online, you will be able to see a copy of those tables online. And another note, if you have elements in their standard state, as defined by having delta F or delta H, F is equal to 0. So most of those will be elements in their standard state. If your enthalpy values are positive, then you can see in this example right here for hydrogen iodide, and again that's a compound, delta H is plus 26.5. And this one will decompose at room temperature into iodine vapor and hydrogen gas. So here's the table. It'll be B14 for enthalpy of formation. And as you look over this, again, hopefully you can get some of these. I don't know that you necessarily need it in your notes, but again, if you are at home, you're going to want to make a copy of this or print a copy of this off of our Google Classroom. Again, some of these that are at 0, you have iodine in its elemental state, hydrogen, those are diatomic elements that are at 0 there. Oxygen is a diatomic element. You can see it's at 0. Carbon in its elemental state is at 0. Depending on if graphite or diamond form, it does have a little bit of a value there in a different form. But you can see some that are largely positive or largely negative. And then we have enthalpy of combustion. So if you're writing down your definitions, it is the enthalpy change that occurs during the complete combustion of 1 mole of a substance. Enthalpy combustion is talking about the breakdown of the reactants, whereas your enthalpy of formation, which are the things we were looking at, we're talking about 1 mole of products that were being formed. So your enthalpy of combustion, you will see delta HC for those values. So this is an example of a calorimeter or a bomb calorimeter, as they are also called. Not all of them look exactly like this, but in general, you do have a larger container on the outside where you have your water, and then in an interior container that has the sample that you're looking at, you'll see the thermometer, so you will have a chance during this reaction that's going on to be able to monitor the change in temperature. And then all of this can be used in your calculations. Now we're going to get into more calculations. This time is how do you calculate your enthalpy of a reaction and your delta H for the reaction. We're going to use Hess's law. And Hess's law states the overall enthalpy change in a reaction is equal to the sum of the enthalpy changes for the individual steps in the process. So the energy difference between reactants and products is independent of the route taken to get from one to another. I will go over an example that shows you all of these steps, but then we'll look at how do we actually condense this down for calculations that we'll do. So in this example, this is the equation that we have. It's carbon plus hydrogen gas is going to give you methane, which is CH4, and you're asked to calculate delta HF. But here's the components. So we have a carbon component, we have the hydrogen component, and then we have the methane component. In this first one right here, you have carbon that is combusting and breaking down. So there's its delta HC, its combustion, enthalpy of combustion. And that value is going to come from table B5. Then you have hydrogen that's reacting. This gives you water. So that is its enthalpy of combustion value from the table. And then you have methane that is also combusting too, and you can see that reaction there. If we were to put all of these together, again, as I'm looking at this right here, our goal was to get back to carbon plus hydrogen, and when we balanced that reaction, it was 2 hydrogens and methane. So that was the balance reaction that you see there. Now if I take those delta H values, well, carbon is in this particular form, so we're going to leave that delta H value there as the negative 393. And then hydrogen also being a reactant, we'll leave its delta H value as negative 285.8, but because there are 2 of these, and we'll get this out, we have 2 of those hydrogens, it's the negative 285.8 multiplied by 2. But then when we get to the methane part of this, in our actual reaction that we have, methane is produced. So in this reaction, that needs to be flipped, which means we're going to flip the sign on the enthalpy of combustion to a positive 890.8. And now we're ready to work with all of those values. Sorry, I got stopped right in the middle of doing this. I'm not really sure where I left off, so I'm just going to say that's the end of this example. We will get to some more examples. So again, if you're using Hess's law, the enthalpy of reaction can be used by calculating the enthalpy of formation. You don't have to know really anything else about the reaction itself. So the overall equation, and you pretty much already have this one written down, the sum of the delta H of formation of your products times how many ever moles, and again, moles is going to be the coefficients that you have, minus the sum of the reactants. In this example, it says calculate the enthalpy of reaction for the combustion of nitrogen monoxide gas to form nitrogen dioxide gas as given by the following equation. So this is our equation balanced. This time they're using a fraction instead of whole numbers all the way across. Not a big deal, but we do need to go look up some data in the appendix again to find out this. So our ones that we're going to focus on as we go to that appendix: nitrogen monoxide, your oxygen gas, and then nitrogen dioxide gas. So as I'm looking at your chart, some things that I see here, we know that we were looking at nitrogen monoxide right here. So again, nitrogen monoxide, if we were forming nitrogen monoxide, it's a positive 90.29. Nitrogen dioxide, for forming it, a positive 33.2. And then oxygen gas, that's in its elemental state, so it is 0. So that will not play a part in our calculations. So if you were to add up these numbers directly as they are, you get a delta H of negative 57.1. Again, this number right here was changed to a negative sign instead of positive because the delta H of formation, that's if we were forming nitrogen monoxide, but nitrogen monoxide is a reactant here, so we're going to change its sign to a negative. It's just the opposite of however it was represented in the chart. If we were to go with the original values, and you were to do delta H of formation is H of your products minus H of your reactants, you would set it up like this. And again, this 90.29 originally, because it was, as far as being formed out of there on the book, it was a positive 90.29. And if you were to look at it now, you would get your negative 57.1. Here's another example. You've got carbon plus oxygen given carbon monoxide. If you wanted to determine the enthalpy of formation, again, these are the values that are going to come from that table. You got your carbon to carbon dioxide, your carbon to monoxide to carbon dioxide. And it says you would reverse the second equation because you need carbon and monoxide as a product. And when you add all that up, you get the negative 110.5. And here's one last example, calculating the enthalpy of formation of pentane. Again, you'll look up your information for it. They're the original values that you should have gotten from your table. Here's those values as you see them now for each part. And if we go with our final equation that we have, your delta HF is negative 145.7 kilojoules.